I'm sure you're aware that for the last year, the Kepler operating science team have been working on a concept of the K2 mission to operate the Kepler spacecraft on 2 reaction wheels. We were invited to the NASA Senior Review over the winter to compete for finances against all of the other astrophysics operating missions within NASA. And last month, we heard that we were successful. We'd been awarded an operating budget for the next 2 years for the K2 mission, and just as importantly, an invitation to return to the Senior Review in 2 years' time, again to compete for more operations.
He has it.
Fantastic.
I
do. Thank you. Now, before I go on, I want to just pause and just thank you guys very, very much, because I believe wholeheartedly that the reason the K2 mission was accepted was simply because of the productivity of scientific communities like yourselves. Just the sheer quantity and quality of science which has come out of the Kepler mission is basically what convinced NASA to continue this adventure with K2. We're almost there. Maybe we can
I think
just
you should
go with that.
go with this.
Yeah.
This will work, and then you'll just have to step down through here.
Thank you very much, technical staff. Yeah. Oh, you want to go with that? Okay. Yeah, okay. Get an extra 5 minutes.
Just continue going. That's another.
There was nothing embarrassing in that. Okay, so you can't see that very well. That doesn't come out very well. But of course, working on 2 reaction wheels, as you know, there is a problem with solar pressure. Solar pressure has this rather horrible feature of pushing the Kepler spacecraft around. So if you don't have 3 or 4 reaction wheels, you cannot point precisely at your field or your targets. And that, of course, has a negative impact on the precision of photometry. Okay, watch this smooth transition. So, and many people have said and still do say, and I often hear them say that the Kepler is using solar pressure to balance that motion, and we're using the sun itself to be the 3rd reaction wheel. And you should stop saying that immediately, because that is not true. What we're doing is pointing in a certain direction towards a direction in our orbital path to minimize the solar pressure upon the spacecraft, so that the solar pressure is almost equally distributed across the spacecraft, to minimize that pressure enough that we can then use onboard thrusters to maintain the precision of our pointing. If we pointed anywhere else out of our orbital plane, which is roughly approximates the ecliptic, we would not have the ability to use those thrusters, which means K2 is finite. It will last as long as we have fuel on board, which will be perhaps 2 to 3 years, or maybe even more if we can find a few more savings. And as you can see on the right there, we can only observe a specific field in the ecliptic for about 80 days. And that's because we need power, and that power is supplied by the solar panels, and they need to be pointing in a range of directions towards the sun in order to give the spacecraft enough power. And we also need to reduce the amount of scattered light through the telescope, and therefore we are restricted to these finite pointings around the ecliptic, which then gives us the possibility to do a whole bunch of pointed surveys in the ecliptic plane. And here you see some color-coded fields, and these are projections. These aren't the real fields. This is just a concept diagram. And you can see that over 3 years here, we're observing a whole bunch of fields along the ecliptic, some passing through or close to the galactic plane, which we pass around twice every year. And this seems like providence, because The one thing we didn't want to do was propose TESS, of course, which NASA's already paying for, and there's no way NASA would pay for it twice. But the fact that the only way Kepler can continue to operate with precision is in the ecliptic plane, where the TESS coverage is at its sparsest, just seemed like complete providence, and this was the way to go. And indeed we did. So, scientifically, what could we do with K2, which we couldn't do with Kepler? The important thing to do to propose to NASA was to do something new and unique that hadn't been done before. Now, of course, if we have a bunch of fields, we now have a bunch of different targets with different properties. Here in the top right here is a map, I believe, of age in the galactic plane and towards a certain direction. And of course, now we can observe a whole bunch of stars of different ages. We can observe a whole bunch of young regions, very young stars. We could in fact do Taurus, which is as young as 2 million years old. So we can do stellar physics, we can do exoplanet detections in a population of 2 million year old stars if we manage to get there. We can do old stars, of course. There are now globular clusters in these potential fields. We can find stars and we can do stellar astrophysics around really old stars around the age of the galaxy. We can do really cool stars. Kepler did very few M dwarfs. We can do a whole bunch of these now. People are very excited about M dwarfs. It's much easier to find planets around M dwarfs often because the stars are smaller, and therefore you can find smaller planets around those stars just because you're looking at this through the transit phenomenon. We can look at bright stars. This is something that Kepler avoided completely. Was bright young stars. And of course, just as George said, bright stars are very important for characterizing planets after we found them. It also gets more exciting because we're passing very close to the galactic center. The microlensing people are extremely interested in K2. Could potentially be looking at Barda's window. So we could be a precursor for the W1st mission and find a dozen or more, several dozen microlensing events with planets around those stars. So we would be finding planets of Earth size beyond the ice line, out around the orbits of the Jupiter-like orbit. And I find it really exciting that we can do extragalactic science, more so now because we have many fields which are above the galactic plane. Where the stellar populations are sparser, and therefore we can use our resources to observe galaxies. And there's one thing Kepler has done, which maybe many of you are not aware of yet, is it's found a whole bunch of supernovae. The great thing about Kepler looking at supernovae is it's not really looking at them, it's looking at the galaxies, and therefore it sees the supernova as they happen, from quiescence to the maximum of outburst, all the way through to decay again. And the morphology shape of those early light curves of supernova basically give you a huge handle on what the supernova progenitor is, which of course is an extremely large and important problem to many communities. And K2 has the ability to find dozens of these things over the next couple of years. More importantly, fundamentally, K2 is very different to Kepler because there is no science team. There is no key science. There is nothing that the Kepler team is going for specifically. K2 is a community facility. What this means is, if you don't propose for it, we won't observe it. It's as simple as that. We sold this mission to NASA for its scientific potential, but we also sold this mission to NASA because it's a community facility. So this means you guys actually wrote the white papers which defined the senior review proposal. We didn't write them. You guys won that case. All fields that we observe, you guys are advocating for. You guys are proposing these fields, and then we're fixing them, and then you guys are proposing the science and the targets. You guys are even choosing the targets because we're doing this through peer review and choosing community members to come in and choose the best science and the best targets. There's no exclusive use period, so this stuff goes straight to a public archive. You guys get this almost immediately. And the one thing I want to talk about at the very end is software, which is going to be an extremely important and very different aspect of K2. So I'm going to go through each of these bullets in a bit more detail. So field advocacy, you guys have advocated so far for the first 6 fields, and these have been frozen now. Field 0 and Field 1 you're probably most aware with. Field 0 was a commissioning field. It crossed the galactic plane. You can see there the ecliptic is the dark black line. You guys, we had it somewhere slightly different. You guys were very vocal and advocated that this field had to be moved so that we included as much of the M35 open cluster as possible, and we did that, and we even put a super stamp over it. So many of our pixels are over M35, which I believe, and somebody shout out if I get it wrong, is the same age as the Hyades. I'm not very good at cluster ages. I'm probably going to make some mistakes over the next few slides. Field 1, which we are observing right now, is in many ways much more quiet and sedate, a little more boring, some people would think. It's far from the galactic plane, but of course we still have many close by stars. We have many stars which are nearby. The M-dwarf population, for instance, is almost identical between these two fields, even though they have very different galactic latitudes. So field 1 was still incredibly popular. We had about 110,000 targets proposed for field 0. We still had about 70,000 targets proposed for field 1. It gets more interesting now. We're now dealing with your proposals for field 2 and field 3. Field 2, of course, covers the upper SCO region. Here we have a whole bunch of stars which range between 5 and 18 million years, I believe. So now we're probing these very young stellar populations for stellar astrophysics and planets. I'm really excited about field 2. Field 3, we're back to a very low galactic latitude now. We're well below in the galactic plane in the southern hemisphere. We have something interesting in there. I believe it's, is it Neptune in the middle? So we have the ability to do seismology of a planet, where we have several proposals to do that, and that's kind of exciting too. So we can do solar system physics now too. Of course, that's also a handicap. You'll notice there's some red lines going through this one. So for both fields 2 and field 3, we actually have Mars passing through the field of view for almost the whole campaigns. So that's going to be a bit of a contaminating factor, I would suggest. And there's not just because of the object itself passing through specific targets, but there's also going to be a huge amount of scattered light coming from Mars and increasing the background in a variable way as the campaigns continue. Fields 4 and 5 are also set, and you guys are going to propose for these things over the next couple of months. The deadline is in August. Field 4 is very exciting indeed. We've got as much of the Pleiades and the Hyades in this field as we could possibly squeeze in. I'm really excited about that. And Field 5 has the Beehive, which I believe is Pleiades age. And we also have this M67 thing down there, which I believe is a cluster of solar age. Also incredibly important. So nobody said I've got that wrong yet, so I'm really impressed by myself, which is fantastic. So those are the fields that we've set. And of course we have many fields coming after that, and you guys still have the ability to advocate through that email there where you want those fields to be, and all the details are of course at that URL. So now we have some milestones, and this is a bit difficult to read at first glance, of course. But so go to the website and try and absorb it. But of course, we have these 80-day campaigns, and basically these purple things are when you propose. So now you're going to have to get used to an almost biannual proposal cycle. And these red triangles are where the data actually arrives in the archive, where you guys can start exploiting the data. So you can see if we're on schedule, the data for campaign 0, all of the objects in that field and M35 will be in the archive hopefully at the end of August, beginning of September. In terms of science, those two campaigns where the science programs have been set are campaigns 0 and 1, and the top two charts there are the proposed topics, if you like, the proposals themselves, and you can see they're spread across the number, the broad science of the Kepler community in almost, in fairly equal ways. It's not weighted towards exoplanets or astroseismology or binary stars. Everybody's getting involved. But then the bottom pie charts there are the targets proposed themselves. And so you can see in both cases they are dominated by exoplanet surveys. And you can see there are slight differences, between the science proposed. There's very little difference between the two campaigns, even though they have very different galactic latitudes. But you can see there are differences in the number of targets. You can see that the extragalactic targets, bottom right there in field 1, they increase dramatically because many more galaxies are known high above the galactic plane and through the galactic plane. And we're going to see this pattern occur, I guess, throughout the mission. Now, the big difference for campaigns 4 and 5 coming up is the proposal process has been fairly relaxed and fairly casual. And to be honest with you, we've been trying to spread as many targets around the communities as possible during the early campaigns. Thank you very much. That's not much time at all. This now has to go through NASA headquarters and is going to be a little more intricate because we suddenly have a vast amount more money to give away. So we have $4 million to give to guest observer communities over the next 2 years, which is fantastic news. Data goes to the archives as normal. These are the two archives that you're familiar with. The light curves, well, if the light curves arrive, the pixels themselves will go to the master archive. Anything planet-wise will go to the NextEye archive. Software, I need to get back to this. We have a round table coming up towards lunchtime. I need to talk about software with you guys, and you need to understand a few things, and we need to come to some arrangements. We're not going to be providing light curves to the archives straight away. It may be that we never provide light curves to the archive. The awkward situation is that K2, because it's running on a much tighter budget, potentially cannot afford the Kepler pipeline, which will be an interesting situation. It may be that you guys are responsible for doing your own data reduction. But you can see here on the right, the good news, and on the left indeed, this is from our commissioning data. The red points on the right there are Kepler G solar type stars. That's our photometric precision over a 6-hour timescale, with timescales of planet transits. That's how good Kepler was, and so for a 12th magnitude star, you were getting down to about 20 or 30 parts per million to find planet transits. The green dots there were just G field stars that we found during the commissioning run that we chose at random, and you could see that we were getting to within a factor 3 or 4 of what Kepler could do. The good news is, after we've done a more careful job of it, these blue dots here is some ensemble photometry. We're now down to a factor 2. The K2 photometric precision, at least of this engineering run, is just a factor 2 from what we were capable of with Kepler. And perhaps we can do better with full campaigns. The reason there's such spread in these blue dots, of course, is because that's astrophysics. The noisiest stuff here is spots. It's solar activity. It's all kinds of stuff. And it's really the floor of that blue sample that you're most interested in there. And very quickly indeed, because I'm being given the 2-minute sign a long time ago, transit injection, Tom Barkley just took those light curves, took a G-dwarf, and just injected some planet transits in there. And you can see that we are very capable of detecting Jupiters in the top left, Neptunes in the top right, super Earths in the bottom left. And we're going to struggle a little bit to do Earths. This is the folding of 4 transits. So we can indeed detect Earths if we get a large number of transits, several dozen transits per target, that we will have the ability to find Earths around some of these objects. And just as a proof of concept, WASP-28 was in the commissioning field. That's a hot Jupiter. There it is there in short cadence. We put a short cadence mask over this. We detected it really well. And here is a serendipitous field star with some kind of transit-like thing in there. We have no idea if it's a planet or not, of course. We have a lot of work to do, or somebody has a lot of work to do to actually validate whether this is a planet or hot Jupiter. But that's now your job. It's not our job anymore. It's the community's job to find these planets and validate them. If you want help and don't know where to go, just go here. This is our job. We will find the help for you. If we can't do it, we'll find the person who can. There's my summary slide. You've heard that all. I won't go over it again. And finally, we are indeed hiring. If anybody wants my job, I'm leaving. I'm moving on up. If anybody's interested in facilitating K2 science, if anybody wants to be the advocate for the community within the K2 project, if anybody wants the K2 engineers from going down the wrong way as far as the community is concerned. If anybody wants to support the community, if anybody wants to push K2 in the right direction, come and see me, come and see Tom, come and see anybody from the Kepler project here. We need somebody good. Anyway, thank you.
Some time for a few questions. In the back there.
It's great, Martin. And I want to thank you guys for everything y'all have done, sort of cobbling this all together. I just have a quick question. These next two fields are going to be really hard to do ground-based, I wouldn't say follow-up, but almost pre-up to find good targets. And I wonder if you've sort of projected for field 6 and 7, and if that's going to be a similar issue, because we'll really only have about a month. We'll be running around like chickens with our heads cut off, trying to get some follow-up for these fields.
I feel your pain. I understand exactly what you're talking about, and it rubs against all of the work that has to be done inside the project as well to set these campaigns up. Indeed, I think it would behoove everybody to try and slow down a bit and make these fields, set them earlier, give people more opportunity to survey them and understand them before they propose targets. But of course, that hasn't been possible yet. I mean, we're already observing field 1. We're on our second major campaign, and we have to prepare for 2, 3, 4. So we're trying very hard to make that delay longer and longer as time goes by. That is one of our goals. And you guys, I know we're missing good science because you guys don't have the ability to observe these things from the ground in advance, but we'll try as hard as we can to stretch that out. It doesn't help that, K2 can point really in 2 different directions. It can either point in the direction that it's moving, or it can point in the direction, in the anti-direction. And we're pointing mostly in the anti-direction because it avoids the Earth, which would whiz through the field every campaign otherwise. But the Earth direction is much more conducive to doing ground-based surveying before each field, and so it's been a hard decision to make. Is it better to, which of those 2 directions is it better to take? And it may be that in future campaigns we flip K2 around so it's pointing in the Earth direction. We certainly will have to do that if the microlensing experiment is going to work, for instance, towards the galactic center. But we'll try as hard as we can.
And we thank again Martin.